Somewhere inside the device you are using to watch this, there is an object smaller than a fingernail that is quietly performing trillions of calculations every single second. It is, without exaggeration, the most complex thing that human beings have ever learned to build. Packed into that tiny sliver of silicon are billions, sometimes hundreds of billions, of microscopic switches, each one far too small to see, all working together in perfect harmony. This is the computer chip. It powers your phone, your laptop, your car, and the vast data centers that now run the world. And in just the last few years, a new and far more demanding job has fallen on its shoulders: to power the artificial intelligence revolution. So what exactly is inside one of these chips? How does a sliver of rock learn to think? And why does modern AI need a completely different kind of chip to run? Let's take one apart and find out. To understand a chip, you have to start with the single most important invention of the modern age, the transistor. For all their dazzling complexity, computer chips are built from billions of copies of this one simple device. And a transistor, at its heart, is nothing more than a switch. Just like the light switch on your wall, it can be flipped on or flipped off. That is all it does. But here is the magic: that on and off can stand for the numbers 1 and 0. And with nothing but ones and zeros, a language we call binary, you can represent absolutely anything. Any number, any letter, any photo, any song, any video. By wiring transistors together in clever patterns, engineers can build tiny circuits that make decisions. Circuits that say, if this and this, then that. The basic logic that all of computing is built upon. Stack enough of these simple switches together, flipping billions of times a second, and you get something that can add, compare, remember, and ultimately, compute. The breathtaking part is the scale. The transistors on a modern chip are almost unimaginably small. They have been shrunk down so far that a single one is now smaller than a virus. You could line up thousands of them across the width of a single human hair, and a fingernail-sized chip can hold tens of billions of them, all packed together in a silent, microscopic city of circuitry. So how do you possibly build something that small? You cannot carve it by hand. No tool is fine enough. Instead, chips are quite literally drawn with light. The process begins with silicon, one of the most common elements on Earth, refined into a flawless, mirror-smooth crystal disk called a wafer. Then, layer by layer, the circuit pattern is projected onto that wafer using beams of light. In a process called photolithography, the light hardens a special coating in precise patterns, and chemicals etch away the rest, sculpting the transistors directly into the silicon. This is repeated over and over, building the chip up in dozens of intricate layers, like an impossibly detailed three-dimensional map of a city, but at a scale measured in billionths of a meter. It is so delicate that it must be done in a clean room, far purer than a hospital operating theater, because a single speck of dust would ruin everything. For decades, engineers managed to shrink these transistors smaller and smaller, roughly doubling the number that could fit on a chip every 2 years, a famous trend known as Moore's Law. That relentless shrinking is the reason the phone in your pocket is more powerful than the room-sized computers of the past. But we are now reaching the very edge of what physics will allow, because the smallest features on a chip are now only a handful of atoms wide. And that looming wall is a big part of why AI changed everything. For most of computing history, the star of the show was a chip called the CPU, the Central Processing Unit, the brain of your computer. A CPU is a brilliant generalist. It has a small number of extremely powerful cores, usually just a handful, and each one is fast and clever, able to handle almost any task you throw at it. But a CPU works mostly in sequence, one complicated instruction after another, in a line. Think of it as a few genius professors, each solving hard problems one at a time, very quickly. For decades, that was exactly what we needed. But then a different kind of chip rose to power. One originally invented for an entirely different purpose: drawing video games. To paint millions of pixels onto a screen at once, this chip was designed to do thousands of simple calculations simultaneously. It is called the GPU, the Graphics Processing Unit, And instead of a few powerful cores, a GPU has thousands of smaller, simpler ones, all working in parallel. If the CPU is a few genius professors, the GPU is an army of thousands of students, each doing simple arithmetic, but all at the very same instant. For most everyday tasks, the professors win. But for one very particular kind of problem, the army is unstoppable. And as it turns out, that one kind of problem is exactly what artificial intelligence is made of. Here is the secret at the very core of modern AI. When an artificial intelligence recognizes your face, answers a question, or generates an image, what is it actually doing underneath? The answer is surprising. It is doing arithmetic, staggering amounts of it. An AI model is built from something called a neural network, a vast web of artificial neurons connected by billions of numbers called weights. And running that network comes down to one operation, repeated on a colossal scale. Take a number, multiply it, add it to another, and pass it along. Multiply and add, billions upon billions of times over. This is the same kind of simple, repetitive math that a GPU's thousands of cores were built to chew through all at once. A task that would take a CPU's few cores an eternity to grind through in sequence, a GPU can devour in parallel. This single insight, that AI is really just enormous walls of multiplication and that GPUs are almost perfectly suited to it, is what ignited the entire AI boom. Chip designers leaned into it hard, adding specialized circuits, sometimes called tensor cores, built for nothing but this multiply and add math, making them faster at AI than any general-purpose chip could ever be. This race has produced some of the most extraordinary chips ever created. Take one of today's flagship AI processors. It packs a barely believable 208 billion transistors. The number is so large that engineers actually slammed into a hard physical limit. There is a maximum size that a single piece of silicon can be manufactured at, and they hit it. Their solution was audacious. They built two enormous chips and fused them together with a connection so fast, moving 10 trillion bytes of data every second, that the two behave as a single giant brain. But raw computing power is only half the battle. The hidden challenge of AI hardware is not the math itself, it is feeding the math fast enough. With billions of calculations happening every instant, the processor sits starved and idle unless data can be delivered to it at blistering speed. So these chips are wrapped in stacks of ultra-fast memory placed right beside the processor, pumping data in at trillions of bytes per second. In fact, this memory bottleneck, simply moving information from one place to another, is now one of the biggest problems in all of computing. And because no single chip is ever enough, they are bolted together by the dozens into refrigerator-sized racks and wired into entire warehouses, humming with thousands of them. Vast AI factories that train the models now reshaping our world. It is worth pausing on just how fast this has all moved. Just over a decade ago, the AI models researchers built had a few million of those internal weights. Today, the largest have well over 1 trillion. That explosion was made possible almost entirely by the silicon, by our ability to pack more and more switches into less and less space. But that road is narrowing. As transistors shrink toward the size of individual atoms, the old trick of simply making them smaller is finally running out. So the next chapter of this story is being written in new ways, stacking chips upward into 3 dimensions, splitting them into smaller connected pieces, and even exploring the use of light itself instead of electricity to carry information. The humble switch is being reinvented all over again, from a single on-off transistor to a fingernail holding hundreds of billions of them, to entire warehouses of silicon teaching machines to see and to speak. The computer chip is the quiet, invisible engine beneath the whole modern world. And perhaps the most astonishing part of all is how we managed to build them in the first place.